All right. So if you look at this kind of purple box there, we've got notation where it says d dx, which stands for our derivative. And we're looking at the derivative of our integral from a to x of little f of t dt is equal to just f of x. Okay, so all they did was take and plug this x in for the function f of t to get this f of x value. That should kind of make sense because if I'm taking the integral and then I'm taking the derivative of that, that's taking and basically canceling each other out, right? So we're just left with that f of x function. Now the second thing, the only thing that's different for the second formula there is that this upper bound is u. So when I plug in u is like a function of x, like it could be x to the fourth power. It's not just x. So I also have to take and multiply by the derivative of whatever that upper bound is, okay? So for this first one, I'm going to kind of show you a little mini proof of how and why it works, and then from there on out, you should be able to answer the rest of them. Okay, so if I look at this first example here, I am going to start by kind of evaluating this inside piece here. Okay, so let's take the integral from 0 to x of t squared plus 1. So the integral of t squared plus 1. If I integrate that, what do I end up with? T cubed. Yeah. Oops, that should be 3. T cubed over 3 plus t. Okay, and if I have an upper and a lower bound, do I need a plus c? No, because what I'm going to do is I'm going to evaluate this at x, and I'm going to evaluate this at 0. So if I plug in this information, I'm going to plug in x for t, and I'm going to plug in 0 for t. I get x cubed over 3 plus x. And then I'm going to subtract what I get when I plug in 0, which is actually just going to be what? 0. Okay. So now this piece right here is technically what's in that parentheses there, right? That's the integral of t squared plus 1 evaluated at x and 0. So now if I went and I took the derivative of what I just wrote, so the d dx of x cubed divided by 3 plus x, if I take the derivative of that, I'm going to end up with this 3 moves down in front. This becomes 3x squared over 3 plus, what's the derivative of x? 1. These 3's are going to simplify out, and I'm just left with x squared plus 1, which if you look back to the original problem here, that's exactly what you get when you take this x and you just plug it in to this function here, x squared plus 1, x squared plus 1, okay? So all you're doing, this derivative and this integral are canceling each other out. They're like inverses of each other. So all we have to do is evaluate it at this point right here and plug that in.
So just changing
Okay.
the t to an x?
Changing the t to an x, exactly, okay? And the reason that this 0 doesn't really matter is because whatever number you plug in, you're just going to get some constant here, right? So like some number, anything, like any number really. And then if I take the derivative of a number, what's the derivative of a number? 0. So that's why the lower bound does not matter, okay? Only the upper bound matters there because I've got that variable, okay? So if I look at the second one here, the second one, I am taking the derivative from 2 to x of the integral 5t minus 3. So again, I don't care about that lower bound, but this x, all I'm going to do is plug that in for t, and we're going to get 5x minus 3 is what I get when I take the derivative of the integral. Okay, now this last example here, it says takes a little bit of a turn when the upper limit is something besides x, as we can see here. If this is not just x, we have to also, after we plug it in, we have to take the derivative of 5x squared. We're doing the chain rule, basically, okay? So again, I'll kind of show you the mini proof here, and then we'll do the easy way for the second one. So if I'm taking the integral from 0 to 5x squared of this function t plus 1, this is technically t squared divided by 2 plus t, right? If I take the integral of that, and I'm evaluating it at both 5x squared and at 0. So if I plug in that 5x squared piece, I get 5x squared divided by 2. Oh, this whole thing is squared though, right? And then plus 5x squared. And what am I going to get if I plug in 0? Also 0, okay? Or again, if it was not 0 down there and it was a number, let's say it was 5, I would just get some number right there, right, where that red is. So that doesn't really matter, okay? Okay, so now this says I need to take the derivative of this. So if I took the derivative with respect to x of my function here, this is 5x squared divided by 2 plus 5x squared. So if I take the derivative of this, I'm going to simplify that 5x squared piece to actually just be 25x to the 4th power. And then the derivative of this piece would end up being 4 times 25 over 2 x to the 3rd plus, what's the derivative of 5x squared going to give me? 10x. Okay, so I can simplify this. That 4 and that 2 is going to cancel to just give me a 2 there. So this becomes 50x to the 3rd plus 10x. Now, if I go back and do it using that formula kind of method, okay, if I plug in this 5x squared, I end up with 5x squared plus 1. Now, this does not equal this yet, right? I need to multiply this by, what is the derivative of 5x squared? 10x. Okay? Now, those two things look a little different, but are they the exact same thing? Yeah, because this just simplifies to give me 50x to the 3rd power plus 10x if I distributed that. Okay? So, if that upper bound is something other than just x, you do have to also take the derivative using the chain rule there to plug that in. So if I gave you something like b, and I asked you to evaluate this, you don't need to do all that work. We can just plug in my 2x cubed where I see t. Just make sure you're plugging it in parentheses here. So I've got 3 times 2x cubed to the 2nd power plus 1. And then this whole thing is going to be multiplied by the derivative of 2x to the 3rd. And the derivative of 2x to the 3rd is 6x squared. Okay, this could be an answer that you leave if it is like a short answer question. If it is a multiple choice kind of question, it might be simplified a little bit more. So like I could distribute this to be, this would be 12x to the 6th power plus 1 times 6x squared, which I could distribute one more time if I wanted to. Again, these are all variations of the same answer. 12 times 6, that's 72x to the 8th plus 6x squared. So all three of these things are the same. So just being able to kind of manipulate it there that way for a multiple choice kind of question. Okay? Questions on that? All right, so that was the end of those notes. If you guys would go grab the U-Substitution notes underneath today's stuff, day 7 in there, and we'll get started on that. So when we were doing the derivatives, the very beginning, we had to use the chain rule, everyone's favorite thing. Now when we're doing integrals, we still have to account for that inside function, but instead of calling it the chain rule, they call it U-Substitution, okay? What that means is we are going to let some function part of our integral be equal to u, and then we will take the derivative of those things in order to replace other parts of our function, okay? So the way it makes the most sense to me, I think, is to just do a few examples, and then you're going to get more confident with what we're going to let u equal. Okay, so if I look at this first example here, we don't know anything about the product rule or anything for integrals, right? The only thing that we know is if we have addition and subtraction, we can separate those, right? So if I look here at this x squared plus 1, that whole thing is raised to the 5th power. So if I asked you like what the inside function would be, you guys would say that x squared plus 1. That's like our inside function to then it's being raised to the 5th power, okay? Another part of our function we have here is 2x. Now, when there is a power outside of our parentheses, that is usually pretty good notation for you to say, okay, the stuff in that parentheses right before is going to be our u. Okay, so I'm going to let u equal x squared plus 1. And we're going to take the derivative of both sides with respect to that variable. So if I take the derivative on the left-hand side, this is now going to become du. And if I take the derivative on the right-hand side, the derivative of x squared plus 1 becomes 2x dx. Okay, so some things that you should be noticing here. X squared plus 1, that's going to now become u. And then do we have a 2x dx? Yeah. So that is now going to become the du piece. Now what I like to do, and this is kind of personal preference, you don't necessarily have to do it like this, but I like to get the dx completely by itself. So I'm going to divide by 2x and make that equal dx. Because now I can take this piece right here that is equal to dx and replace it with dx. So that way things can simplify out. Okay, so I'm going to rewrite my integral now with everything that I'm replacing. So this is now the integral of u to the 5th power times 2x. And then instead of dx, I'm going to write this as du over 2x. Okay, so my 2x's, those are going to go away, right? And now we're going to integrate u to the 5th power du. Can we do that? Can we take the integral of that? Yeah, the integral of u to the 5th power is just u to the 6th power divided by what? 6 plus c. Okay, well, we said earlier that u here is equal to x squared plus 1. So now I'm just going to replace that with where we see u. So our final answer is going to be, x squared plus 1, that is all raised to the 6th power, divided by 6, plus c. Okay. Now we can double check our work, which is kind of the cool part about math. Okay. If I go and take the derivative of this thing that I just highlighted there, I should end up with exactly what I had at the beginning. Okay, so I'm going to show you that step. If I take the derivative of this piece right here, this would become 6 times x squared plus 1 to the 5th power, still divided by 6. But if I take the derivative, that means I also have to take the derivative of this inside piece. So the derivative of x squared is 2x. Now if I simplify this, the 6 goes away, and I'm left with x squared plus 1 to the 5th times 2x, which is exactly what I have over here, is what we ended up with when I took the derivative. Okay, so it's using the chain rule, but we call it U-substitution because we have to let something equal u in order to integrate it. Otherwise, we won't be able to integrate things that we're multiplying together. Okay, so we got to think about different ways that we can manipulate the equation. Okay, like how on that homework you guys had to use the trig identities. Okay, that's a way to kind of manipulate the equation. Next class, we're going to talk about completing the square, long division. Okay, different ways that we can manipulate the equation in order to take the integral of both sides. Okay. Okay, let's look at this next one here. This next one, I've got x squared times 2x cubed plus 5 to the 4th power. So I've got kind of two different things going here, right? I've got this x squared, and I've got 2x cubed plus 5, and this is raised to the 4th power. So there's really like two things that you could potentially let u equal, but only one of them is going to get you to the right answer. Sometimes you could let u be different things and you're going to end up getting the same answer regardless, okay? But let me show you really quick what happens if I let u equal x squared. I would not write this down, okay? if u is equal to x squared and I take the derivative of both sides, I get du is equal to 2x times dx. Okay, if I replace this u for x squared, I have this whole thing 2x cubed plus 5 to the 4th power, and all I have that's going to cancel out is 2x dx. Is that even going to be there? Can I cross out a 2x here? No. Okay, so that's not going to be very helpful. So we got to think a little bit differently. Again, usually the one that has an exponent there is going to be your function that you're going to let u equal. So this thing right here, if I let u equal 2x to the 3rd plus 5, and I take the derivative of both sides, the derivative of 2x cubed plus 5 is going to be 6x squared dx. And now if I take and solve for dx, I get du over 6x squared is equal to dx. Is something going to simplify out now? Yeah. So let's rewrite my integral in terms of u and my du. Okay, so this is now going to become the integral of x squared times u to the 4th power. And then instead of my dx piece, I'm going to write du over 6x squared. And now what's going to simplify? My x squareds. Those both go away. And I'm left with the integral of u to the 4th power du. And then that 6, don't forget that 6 down there. I'm going to write that as 1/6 on the outside. Okay? Because any constant is always going to be part of my integration after I integrate that function. Okay, so now from here we can integrate this. What's the integral of u to the 4th power? Yeah, u to the 5th over 5. And then I've got that 1/6 in front. So times u to the 5th divided by 5 plus c. So this becomes u to the 5th divided by 30 plus c. And for my final answer, I just got to plug in what u is equal to. U was originally 2x cubed plus 5. So this is 2x cubed plus 5, all raised to the 5th power, divided by 30 plus c. Okay. Again, we can double check our work. If I take the derivative of what I just had, okay, the derivative would be 5 times 2x cubed plus 5 to the 4th power. This is all divided by 30. And then I'd have to take the derivative of the inside piece, which is actually 3x squared. Oh wait, sorry, I can't multiply. 6x squared. And if I simplify this, that 5 times 3 is 30, so that's going to go away. Did I end up with what I started with originally? Yeah. Okay. Questions on those two? Okay. These next two, we got square roots. Again, just like I said, when you have something underneath a power, think about it, same thing for square roots, right? The stuff underneath my square root is technically raised to a power, right? So I would let that be my u, okay? So if I let u equal x squared plus 3, my du is going to equal 2x dx. And if I solve for dx, I get du divided by 2x is equal to dx. And now I can go ahead and replace stuff. I want you guys to rewrite this. This is going to be my u. Rewrite my dx is equal to du over 2x. And see if you can't simplify that. Okay, so when you replace it, your integral should look something like this. The integral of x times the square root of u times du over 2x. Okay? And now those x's are going to go away. And I'm just left with the integral of the square root of u du with a 1/2 in front. And now this is something that we can integrate. We can think about this as the same thing as the integral of u to the 1/2 power. So if I integrate this, I'm going to have 1/2 times what? What am I going to end up with for my integration on that? Yep, u to the 3/2 power divided by 3/2 plus c. Now let's simplify this fraction and fraction mess here. This is technically 1/2 times 2/3 times u to the 3/2 power plus c. Or my 2's go away, and I'm left with 1/3 u to the 3/2 plus c. But what does u equal? X squared plus 3. So I got to replace that for your final answer to give us 1/3 times x squared plus 3 raised to the 3/2 power plus c. Again, if I wanted to check my work, I can take the derivative of this thing, and my derivative of this should end up giving me what I took the integral of. Okay? All right. Do you guys think you could try out this third one, or this fourth one by yourselves? Cool. What are we going to let u equal so that we make sure we're on the same page? 3x squared plus 4. Go ahead and try out that fourth one. All right, do we all agree with that answer of 1/3 times 3x to the, oh, I forgot a 1/2. That should be to the 1/2 power plus c. Do we agree with that?
Yes.
Yes? Okay, wonderful. Moving on, next page. Okay, if you look at all of these all have what in common? Trig, right? So we gotta think a little bit differently for these ones. Again, if there's anything to a power, so like this second one, this is technically sine of x to what power?
3.
The third, right? But up here, I don't have anything to a power. So what am I gonna let x, or what am I gonna let u equal in this case? I'm gonna let u equal 3x. Yeah, it's kind of like what just your gut tells you. It's probably right. So I'm gonna let u equal 3x here. And if it doesn't work, then we could try something else. But let's let u equal 3x. If I let u equal 3x, what is the derivative gonna give me? 3 times dx, right? So then I can rewrite this as du over 3 is equal to dx. Okay, really quick, don't write this down, but I do just want to show you. If I let u equal cosine of 3x, if I let u equal that, well, what is the derivative of that going to give me? What's the derivative of cosine? Negative sine times 3x, right? But then the derivative of 3x would be 3. Is that going to help me simplify anything out? No, it's going to make it way harder for us, okay? So double check. I mean, that's gonna kind of be a check right there. If this doesn't help us, we're going to have to try something else, okay? So I'm going to replace this stuff. I've got the integral of cosine of u times du over 3. So I can just rewrite this as 1/3 times the integral of cosine of u du. And what is the integral of cosine?
Sine.
Yep, the integral of cosine is just sine. So I've got 1/3 times sine of u plus c. And then all we got to do is plug in my u value. So this becomes 1/3 sine of 3x. Okay. Questions on that one? Yeah. Next one, I've got sine cubed of x, cosine of x. So this is the same thing as sine of x cubed times cosine of x. I've got two functions here. If I let u equal cosine of x, what is the derivative of cosine of x? Negative sign. That would get rid of one of my signs, but would it get rid of all of them? No. So again, if you have something and it's raised to a power, almost always, that is going to be what your u value is equal to. So this is going to equal u for our u substitution. So u is equal to sine of x, which means du, the derivative of sine, is cosine of x dx. And then this would be du divided by cosine of x is equal to dx. Okay, so now I can rewrite my integral. My integral is now u to the third power times cosine of x times my dx piece, and dx is equal to this du over cosine of x, which is going to nicely cancel out my cosines. And now all you have to do is take the integral of u cubed du. What's the integral of u cubed? U to the fourth over 4 plus c. And to end it there, what do I got to do? Plug in your u. Oops. How did I do this? Oh, sorry, I opened some weird tab on my thing. So yes, this becomes sine of x to the fourth power divided by 4 plus c. Okay, now be careful with how you write sine of x to the fourth power, because this is not the same thing, what I wrote there, and this would be okay, but do not just leave it as sine of x to the fourth power like that. Okay, either one of those two is fine, but don't have it be to the fourth power on the outside there without parentheses. Okay. All right. This next one, very very similar. The only thing that's different is that there's a 5x on the inside there. So what do we think our u is going to equal for this integral? Sine of 5x. Okay. So let's let u equal sine of 5x plus u, which means that the derivative plus u is going to also equal cosine of 5x, but times what? 5. Times 5. Okay. And don't forget that dx. So if I solve for dx there, now I can replace that stuff in my integral. So I'm going to let you guys finish this one out, and then I will put the answer up here in a few minutes. All right, double checking. Do we all get sine of 5x in parentheses to the fourth power divided by 20? Plus c. Yes, thank you. I always want to forget the plus c as well. Okie dokes. Make sure that 4, if you wrote that 4 here, that would also be fine. But if you write the 4 without the parentheses and just wrote it right here, that would be incorrect, okay? Because then it would be like 5x is to the fourth power, and you're taking the sign of that function, so just be careful for that one, okay? All right, this last example, we are not going to do this differential equation one, so you can go ahead and cross that one out. What does our gut tell us that maybe u should equal? Cosine of x squared? Yeah. Do we think? Cosine of x squared? Because if I take the derivative of cosine, what am I going to get? Negative sine. Oh, what did I write? I said d is equal to? I meant u. U is equal to that. So then if I take the derivative, negative sine squared, or sine of x squared, and then times what? Chain rule says 2x, right? So go ahead and finish this one, plug in all of your stuff, see where things cancel out, and I will show my work up here in a minute. Once I get to this point, things should start simplifying out. This sine of x squared goes away, x goes away with that x, and I am left with the integral of u to the fourth power. But then I also have this negative 2 down here, so I'm going to rewrite that as negative 1/2 on the outside. And then I can take the integral of this. This would be negative u to the 5th over 2 times 5 plus c, which is the same thing as negative u to the 5th over 10 plus c, and then I just got to plug in the u. So I'd have negative cosine of x squared. And now, does the negative go in the parentheses? No. So just the cosine of x to the 2nd power goes in parentheses. That's all raised to the 5th power. Divide that all by 10 and add c. Okay? Questions on any of those? Okay. Again, don't forget everything that we already talked about for integration. Like if I had things like the integration of x squared plus 7x divided by x dx. Okay, actually that was kind of a bad example because you technically could do u-subs. Let's say this was the square root of x, okay? We did one like this 2 classes ago. How would I rewrite something like this? Yeah, x to the negative 1/2 times that by x squared plus 7x, right? And then take the integral of that. Because if I have things that are separated by an addition or subtraction sign, I can take the integral of each individual piece and then add those together or subtract those, right? So don't forget what we've talked about already. You only use U-substitution when it's something you can't do without it. Like there's multiplication involved, so you have to cancel something out so that you can take the integration of both sides, okay? All right.